Alright, I'm going to look a little bit more in detail about finding the area between two curves. We definitely know how to find the area under a curve. We've talked about that extensively. And we've talked about net signed area and what it means to have a negative definite integral value and a positive one. What I have set up here is two functions f and g, where f is above g. And what I want to do is I want to find the area enclosed by them, in between them, between x equals a and x equals b. So since I know how to find the area under a curve to the x-axis, I could simply take the area under f, which is everything you see in blue here, the definite integral from a to b of f of x dx. And then I could take away the area under g, which is what I have here in green, and I would get my area in red. Now if you just take a look at this expression here, by the properties of definite integrals, I could combine that integral to read definite integral a to b of f of x minus g of x dx. And what I want you to think about is just another way to interpret this answer. This f minus g can be thought of as the height between the two curves. So you have your two curves here. This distance, it's the y distance of the top minus the y distance of the bottom, gives you the height of the rectangle times its thickness. So what I'm suggesting is that we don't necessarily need to do two integrals to find the area between them. We can simply do one by thinking of the height as the top minus the bottom function, because that will give us a positive height times its thickness. Now a natural question would be, does that always work, even if the curves were, both below the axis or both above the axis? And the answer is yes. Let me just take one of those questions. What if I had f above and g below? And I wanted to go f minus g. Well, keep in mind that f would represent, let's take a given value, f would represent this value, g would be a negative value from the x-axis down, and if I therefore go this, take away this negative value, what I will get is this entire length as a positive quantity. So in fact, as long as you're taking the top minus the bottom, this will represent the height of the rectangle and dx its width. So just to extend that to a simple example, if I had these two functions and I wanted the area between them, and I want the area between x equals 0 and x equals 4, if I run my rectangles vertically, the square root function is always on top, the line is always on the bottom, so I'm always taking the higher minus the lower, so my rectangle lengths will be positive. Remember, if I'm doing area, I want it to come out to be positive, so my heights need to be positive. So if I take the top function minus the bottom function, that's the height of each rectangle at any value of x that I'm at, times the thickness of each rectangle, sum up all rectangles running from x equals 0 to x equals 4. And you can calculate that through the first fundamental theorem, or using your calculator, you're going to get 22 over 3. Okay, here's another example that's a little bit more complex. I want to find the area shaded in red. So if I run my rectangles vertically from left to right, from -2 to 2, I'll notice that until I get to the y-axis, my height is determined by the top function, which is the root of 2 minus x, minus the bottom function. After I pass the y-axis, though, my height is simply the height off of root 2 minus x. So what I'm saying here is that we're going to have to break the area of this up into two sections. We're going to integrate from -2 to 0, top function minus bottom function, times thickness. And then between 0 and 2, it's the top function, and the bottom function, you can think of it as y equals 0, so minus 0. times dx. And that will give me the shaded region. And if you work that out, that is 10/3. Now I want to look at this particular problem in a different way, because the way we did it, we had to break our integral into two parts because the bottom function changed once we got to the y-axis. So what we're going to do this time is run rectangles horizontally. So infinitely thin rectangles running this way. So if I have an individual rectangle, to get its area, I'm going to do its width, which is a piece of y this time, and its length will be the x distance of the one function minus the x distance of the other. When we ran them vertically, remember it was the y distance of the one minus the y distance of the other. The y was with respect to x, but it was the y distance of this one minus the y distance of this one in order to get the distance between them. So now we're going to take the x distance of one minus the x distance of the other to get the height of an individual rectangle. And instead of taking the highest minus the lowest, it's still going to be the highest minus the lowest, but because we're running our rectangles horizontally, that's going to be the right value minus the left value. What this is going to mean is, since we're subtracting two x values to get this length, we need to have our functions isolated for x. So this would be x equals negative y, and if I square both sides and rearrange, I'm going to get that to be x equals 2 minus y squared. My integral I'm developing will be with respect to y, because thickness is a piece of y, and because to get the heights we have to subtract two x values, and therefore x must be isolated, so we can take this value minus this value in terms of y. Just to try to make that a little bit clearer, for my first rectangle, which is situated at y equals 0 right here, when y is 0, the height of this would be a y value of 0 in this equation, which would be 2 minus 0 squared, which would be x equals 2. And you can see that the height indeed is x equals 2. Okay, let's just look at one more rectangle to make sure you understand what's happening. So in terms of finding the length of this rectangle, I'm going to take the x distance of the first function, which is represented by this quantity here that I'm scribbling, minus the x distance of this other function with respect to y, and that's going to give me a positive value here. So if I take the function furthest to the right, 2 minus y squared, which again represents this distance here, minus negative y, which is this distance here, times the thickness of the rectangles, dy, and I integrate that from y equals 0 to y equals 2, I will get the area. And I should get the same area that I was able to get when I did the rectangles running vertically. Alright, so let's just clean up this equation a bit. That would be negative y squared plus y plus 2 dy. If I go over to my calculator, now since I'm doing this with respect to y, I'm just going to think of my y's like x's when I type it in, since the calculator requires me to use x. And do I get 10/3? Yes, I do. So as you can see, in some situations it's easier to run rectangles horizontally, which means that your integral will be with respect to y than it is to run them vertically when your integral is with respect to x. Alright, so let's just generalize this result for horizontal rectangles. If you've got two functions f and g, where f is to the right of g, so f of y meaning that we've got both of our functions isolated for x, f of y is greater than g of y, and we're going to do the area between y equals c and y equals d. If we run our rectangles horizontally, our thickness will be a piece of y, and our length will be the x distance on f, keeping in mind that that's with respect to y, so it's f of y, this distance, minus g of y, which is this distance, to give me my distance here, times thickness dy, and summing up all the rectangles running from y equals c up to y equals d. Okay, so let me just write that so you can see it clearly. The area would be integral from c to d of f of y minus g of y, rightmost function minus leftmost function, which gives you the height of the rectangles, times thickness dy.